This is the 18th in a series of videos that I'm creating to support a course in elementary number theory. We've just talked about primitive roots in some previous videos and when there exist primitive roots mod n, and now we want to look at some applications of primitive roots modulo n. But before we do that, I want to recall the definition as well as prove a nice proposition which will help us use that application. Okay, so we say R is a primitive root modulo n if one of these two equivalent things is satisfied. So first, the order of R mod n is equal to phi of n. Remember that the order is the smallest non-negative integer, so that when you raise R to that number, you get 1 mod n. But that's equivalent to saying that if we take R to the k for all possible k, notice I've kind of overdone it here. We really only need k to go between 1 and phi of n. Then you get the same thing as the set of all integers from 1 to n that are relatively prime to n. And I should say this is all working modulo n. Okay, great. So now we're going to look at the following proposition, which will set us up with some tools in order to solve some nice congruences. And that is R to the A is congruent to R to the B mod n, if and only if A is congruent to B mod phi of n. So in other words, if the bases are acting mod n, then the exponents are acting mod phi of n. Okay, so let's maybe see how this goes. So we'll do this forward direction first. So in other words, we want to suppose that R to the A is congruent to R to the B mod n. But now let's notice that that tells us that R to the A minus B is congruent to 1 mod n, where we just multiply by R to the minus B. If you're a little bit worried about this, you can just assume that A is bigger than or equal to B. Okay, so from here, we see that the order of R divides A minus B. But let's recall that the order is phi of A, given the fact that R is a primitive root. So we know phi of n divides A minus B. But that's equivalent to saying that A is congruent to B modulo phi of n. Okay, so that's how the proof of that forward direction goes. Then how would we do the reverse direction? Well, it's essentially the same idea. So if we start with A is congruent to B mod phi of n, then that means that we can write B as A plus K times phi of n. And then notice that R to the B is the same thing as R to the A times R to the phi of n all to the k, just using exponent rules. But this R to the phi of n is congruent to 1 mod n, and that's given that R is a primitive root, or just by Euler's theorem, so we know that is congruent to R to the A mod n. So that proves that reverse direction. Okay, so now that we're armed with this proposition, which let me reiterate the importance of this. If the bases are calculated modulo n, the exponents are calculated mod phi of n. Now let's move on to some examples. So for our first illustrative example of the use of primitive roots, we'll solve x cubed is congruent to 5 mod 17. So clearly there's kind of a quick way to do this just with guess and check. Since 17 is not really that large of a number, we can just calculate 1 cubed, 2 cubed, 3 cubed, so on and so forth until we get something that is congruent to 5. But that's not really in the spirit of using primitive roots. So let's do it maybe this more lengthy but more systematic way involving primitive roots. So our first step here will be to find a primitive root mod 17. Okay, well, how do you find a primitive root mod 17? Well, let's recall that R is a primitive root mod p if and only if r to the p minus 1 over q is not congruent to 1 mod p, and this is going to be for all primes q that divide p minus 1. So in other words, what we need to do is look at all prime divisors of 16 and then make this calculation of r to the 16 over that prime divisor. Well, we're in luck here, and that is because the only prime that divides 16, which is equal to 17 minus 1, is 2. So the only thing that we need to check in order to have a primitive root mod 17 is r to the p minus 1, so that's going to be 16 over 2, and see if that's congruent to 1 mod 17 or not. So we want this to be not congruent to 1 mod 17. So we'll just run through some picks for r until we find something where it's, like I said, not congruent to 1 mod 17. And then we'll have a primitive root. And if you're wondering where this trick came from, I think we proved it at the end of the last video. Okay, so let's first see if 2 is a primitive root mod 17. Like I said, all we need to do is look at r to the 8 here, or 2 to the 8. So let's look at 2 to the 8 mod 17. So let's notice that 2 to the 8 is the same thing as 2 to the 4 squared. So there's like a lot of different tricks for reducing the complexity of calculating these powers, but really you just have to kind of get a feel for which trick to use. And I would say just doing a lot of practice here. I find myself getting better and better at doing these kind of tricks for reduction as I teach this kind of course more. So I wish I had a more systematic way to practice it, but I think you just really have to drill lots of problems like this. Okay, so like I said, we want to calculate 2 to the 8. But by exponent rules, that's 2 to the 4 squared. But notice that that is equal to 16 squared. But 16 is congruent to minus 1. So that's negative 1 squared, where we're working mod 17. But that is congruent to 1 mod 17. But remember, we want this to not be congruent to 1 mod 17. So that means that this 2 is not a primitive root. So let's move on to the next number. We should probably move on to 3. That would be a good next choice. Now, there is some discussion about how often 2 is a primitive root that you can look into. There isn't a strict proof as to the percentage of primes that allow 2 to be a primitive root, but there are some conjectures. I'll let you guys look that up if you want to. Okay, so let's check if 3 is a primitive root. So just as before, we need to calculate 3 to the 8. We hope that that is not congruent to 1 mod 17. So let's notice that that is the same thing as 3 to the 3 times 3 to the 3 times 3 to the 2. Okay, but notice that 3 to the 3 is 27, but 27 is the same thing as 10 mod 17. So this is the same thing as 10 squared times 9 mod 17. But then next we can check that 100 is negative 2 mod 17, making this whole thing negative 18 because it's negative 2 times negative 9. But negative 18 is going to be the same thing as negative 1 modulo 17. But notice that negative 1 is not the same thing as 1 mod 17, so that means yes, we're good to go. We have a primitive root mod 17. Okay, so let's bring that up and then we'll finish this problem off. Okay, so towards solving this example, we have so far determined that 3 is a primitive root mod 17. Next up, we want to write x cubed and 5 as 3 to some power. Then how would you write 5 as 3 to some power? We'll get to x cubed next. Well, really, it's just by making a chart of powers of 3. So I will admit that this step is a little bit grindy, but sometimes you have to do that. So let's maybe write it like this. We'll have k and then 3 to the k, keeping in mind that we're calculating all of this mod 17. So we'll look at just some first powers of k. I'm not going to go very far because I know where this is going to end. Okay, so 3 to the 1 is 3. 3 squared is 9. 3 cubed is 27, but let's recall that 27 is the same thing as 10 because we're working mod 17. Okay, but now we can take 3 to the 4th. That's going to be the same thing as 3 times 10, which is 30. But then 30 is 4 less than 34, which is 17 times 2. So this is the same thing as -4. That might be a little bit easier to work with. We could also see that -4 is 13. Okay, so now if we multiply that by 3, we'll get -12. But notice -12 is the same thing as 5. But 5 is exactly what we're aiming for, because that's the right-hand side of this congruence, so we can stop here. So notice that tells us that 3 to the 5 is congruent to 5 modulo 17. Okay, nice. But now how do we write x cubed as a power of 3? Well, notice we've got a variable there, so we have to have a variable in our rewriting as well. So let's start by writing x as 3 to the y mod 17, but that tells us that x cubed is 3 to the 3y modulo 17, just using exponent rules. Okay, and now where do we go from there? Well, we're going to take our goal congruence and rewrite it using these two things that I have underlined in orange. And that comes to our last step, which is essentially just solve. So now we have 3 to the 3y is congruent to 3 to the 5 mod 17. Okay, but now we can take everything out of the exponent if we calculate phi of 17. So now we have 3y is congruent to 5 mod phi of 17, which is 16. Now we can multiply both sides by 3 inverse mod 16. Notice 3 inverse will be equal to 11. That's because 3 times 11 is 33, which is 1 more than 32, which tells us that y is congruent to 55 mod 16. But we're not quite done yet, because notice 55 mod 16 can be reduced. Notice that can be reduced to 7 mod 16. So we have y is congruent to 7 modulo 16. But that's not our original goal. Our original goal is to find x. Well, how could we find x? Well, we take this value for y and plug it in up here. So that means x is congruent to 3 to the 7 mod 17. We're working mod 17, mod the base instead of mod the exponent. But now we can continue our chart here to figure out what 3 to the 7 is. So if 3 to the 5 is 5, that means 3 to the 6 is 15. Notice that 15 can also be written as -2, which is maybe a little bit easier to work with. That means 3 to the 7 would be -6. But notice -6 plus 17 is equal to 11. So in fact, the number that we're looking for here is 11. So this is congruent to 11 mod 17. And there we've got a solution. And then you might say, well, by Lagrange's theorem, we could have up to 3 solutions to this. But here we only have 1. But that's okay, because we got down to this point right here, and we see that we have a single solution to this linear congruence. And you could imagine a place where you have more solutions to this linear congruence, and that would produce more solutions to our original congruence. Okay, so now that we've got this taken care of, let's look at another example. So for our next example, we'll solve an exponential congruence. So we want to determine the solution to 5 to the power x congruent to 17 mod 19. Again, we use primitive roots. So we first have to find a primitive root. A good place to start is with the question, is 2 a primitive root? But before we answer that, and that's how we will continue this problem, I want to also point out that another kind of obvious choice would be to decide if 5 was a primitive root. Because if 5 is a primitive root, then the left-hand side of this congruence is already taken care of. As a warm-up, I'll let you guys decide if 5 is a primitive root, which would allow us to skip some steps here. Okay, but we're going to answer the question, is 2 a primitive root? So I first want to notice that we need to look at the primes that divide phi of 19 or 18. And that's by our test for primitive roots that we talked about in our last example. There are only 2 primes that divide 18, and those are 2 and 3. So that means we've got a little bit more work than we had last time, but not too much. Okay, so let's calculate 2 to the 18 over 2 mod 19, and then 2 to the 18 over 3 mod 19. Our hope is that neither of these is congruent to 1 mod 19, which would mean that 2 is a primitive root mod 19. Okay, so this one is 2 to the 9, obviously, because 18 over 2 is 9. Then we can calculate this as 2 to the 4 squared times 2 to the first power. So just using exponent rules. So let's notice that 2 to the 4 is 16. So we have this is 16 squared times 2. But we're working mod 19. So let's recall that 16 mod 19 is -3. So we have this is -3 squared times 2. -3 squared is obviously equal to 9 times 2 is equal to 18. So this is 18 modulo 19. But that is not 1 mod 19. So the chance of 2 being a primitive root is still alive. Okay, let's calculate this. So let's see that that is 2 to the 6th power. Maybe we would want to calculate that as 2 to the 4 times 2 to the 2. Well, notice 2 to the 4 is 16, which is -3 like we talked about before. So this is the same thing as -3 times 4. 2 to the 2 is obviously 4, but notice that that is congruent to -12. But -12 is congruent to, let's see, 7 mod 19. So that's also not congruent to 1 mod 19. So yes, 2 is a primitive root. So the next thing to do is probably to make a chart of all of the powers of 2 mod 19. So let's get the bones of the chart on the board right here, and then we'll fill it in. So I got the skeleton of the chart of powers of 2 mod 19 on the board. So let's notice that we know 2 to the 6 is 7 and 2 to the 9 is 18 by what we calculated up here while testing if 2 was a primitive root. Now we want to fill in the rest of this. And also notice, because of Fermat's theorem, I only need to work between values of k from 1 to 17. We know 2 to the 0 is 1 and 2 to the 18 is 1 as well. Again, by Fermat's theorem. Okay, so let's get into the filling up of this chart. So 2 to the 1 is 2, 2 to the 2 is 4, then we have 3 here, we have 16 here. Notice that 16 is the same thing as -3. So that means 2 to the 5 is going to be -3 times 2, which is -6, which is 13. Again, we already decided that 2 to the 6 was 7 by this calculation. That means 2 to the 7 is 14. Notice 14 is -5. Because it is 5 less than 19. Multiply that back by 2, we get -10. But -10 is congruent to 9 mod 19. And now here's a little bit of a trick, because this guy right here is equal to -1 mod 19. And everything from there to the end is exactly the entries that we have here multiplied by -1. Then that means we can just find the negative residues of each of those, and we'll fill in all of those boxes. So just to reiterate, 2 to the 10 is the same thing as 2 times 2 to the 9, which is negative 1. That makes it equal to negative 2. But notice negative 2 is the same thing as 17. Then likewise, we'll have negative 4 right here. But negative 4 is the same thing as 15. We'll have 11 here because that's the same thing as negative 6. We'll have 3 here because that's the same thing as negative 16. And then just filling in the rest, we'll have 6, 12. 12 times 2 is 24, which is the same thing as 5. And then finally, we'll have 10 for the last one. So this fact that we've got a minus 1 in the middle is really helpful. We only have to calculate this first half, multiply this first half by minus 1, and then take the appropriate positive residue. Okay, so now let's jump back to our example. We want to solve 5 to the x is congruent to 17 mod 19. So notice 5 to the x can be rewritten as, well, let's see where 5 is as a power of 2. It's going to be 2 to the 16 times up to the x. Again, that's from our chart here. We're honing in on this portion right here of our chart. Okay, but notice that's the same thing as 2 to the 16x using exponent rules. But now let's look at 17. So we need to find 17 on this chart. Notice that's the same thing as 2 to the 10. So we have this is 2 to the 10. And like I said, that's from this portion of the chart right here. That means we can take our original congruence and rewrite it as 2 to the 16x is congruent to 2 to the 10 modulo 19. Then pulling the exponents down, we see that this means 16x is congruent to 10 mod 18. If we pull the exponents down, we have to apply phi to this number right here. But now let's notice that all of those are even. So that means we can divide them all by 2. So we can divide this by 2, we'll have 8, this by 2 we'll have 5, and this by 2 we'll have 9. So we really need to solve 8x is congruent to 5 mod 9. But let's notice that 8 is its own inverse modulo 9. That's because 8 is equal to negative 1 mod 9. So we can multiply both sides by 8, and we'll have x is congruent to 40 mod 9. But let's see, 40 mod 9 is the same thing as 4 mod 9. So there we have a solution. X is 4 mod 9. But we got that solution from this simplification here. But our solution should be mod 18, not mod 9. So that means, in fact, we have two solutions. We have x is congruent to 4, or it is congruent to 4 plus 9, which is equal to 13 modulo 18. And again, we got two solutions here instead of one because we simplified this congruence by dividing by 2. And just recall by the theory of solving linear congruences that sometimes you have more than one solution when you do something like that. So again, we've got two solutions there. X is congruent to 4 or 13. Okay, so now let's maybe get rid of this and I'll leave you guys with a couple warm-up problems. So here are two quick warm-up problems that are built off of the information that we saw in this video. So they're to solve the following two congruences. So we've got 3x to the 14 is congruent to 2 mod 23, and then 13x is congruent to 5 mod 23. And that's a good place to stop.